Welcome to today's lesson on logarithmic functions. Let's begin in topic 1 and review a little bit of work with exponents and a base of 10. If you have 10 cubed, that is simply 10 times 10 times 10, which would be 1,000. So you would have 3 zeros in your number. If you look at a negative exponent, we can make a negative exponent positive by simply moving 10 to the bottom of the fraction. So that would make 1 over 10 to the positive 1 power, or just 1/10. The same would hold true on number 5. You could rewrite this as 1 over 10 cubed, which would then be 1 over 1,000. On number 6, 10 to the 1/2 is a little different. Anytime your exponent is a fraction, this becomes a radical. 1/2 would be a 2 on the hook, which is just a square root. If it had been like 10 to the 1/3, that would be a cube root. And then you would put your 10 under the radical, referred to as the radicand. Let's move down to number 15. Here we discuss an exponent of 0. It is important to note that anything to the power of 0 equals 1, except 0 to the power of 0 is undefined. Looking at number 14, 4 squared is 16, but 4 to the power of 0 is 1, giving a result of 15. Number 15 is a little tricky because take note that this is 4 times x to the power of 0, which is 4 times 1, which is 4. Let's move down to some solving situations. Notice in topic 3, we have equations. So once we convert to an equation, we will then be solving. So in these examples, we're solving for the variable. In number 17, we have 5 to the power of y equals 5 to the power of 1. If we get the bases the same, there's a rule that says we can then set the exponents equal. Y equaling 1 would be your solution. Moving to number 21, we have a 9 and a 3. We would like to have a base of 3. So I need to get this 9 rewritten as a 3 squared. Now the left side of the equation is 3 to the power of 2y, and the right side is 3 to the power of 1. My bases are now the same. So I can use the property to set the exponents equal, giving me a solution of y equaling 1/2. Looking at a similar example, number 22, I see a base of 2 and the number 16. I need to convert 16 to be written as 2 to an exponent. So the left side is 2 to the power of y, and the right side is 1 over 2 to the power of 4. So now I have a base of 2. I'm going to rewrite the right side as 2 to the power of -4, because when I move to the opposite side of the fraction, it changes the sign on the exponent. At this point, with my bases the same, I can set the exponents equal, resulting in my solution. Let's look at number 27. I have a 3 and a 9. I'm going to try to get everything as a base of 3. It is most common that you will see examples where you will change the base to a 2, a 3, a 4, or a 5. So again, in this case, I want to convert to a 3. Well, the left side is 1/3. If I move the 3 to the top of the fraction, it would be written as 3 to the power of -1. The 9 on the right side of the equation is 3 squared. So at this point, I have the same base of 3. The left side is 3 to the power of -y, and the right side is 3 squared. With the bases the same, I set the exponents equal, and then come up with my solution that y equals -3. I'm going to move down actually to the next page where we're connecting to college algebra. Here is where we finally see logarithms. And the first skill you need to develop is being able to convert a logarithmic equation to an exponential equation and vice versa. The first topic here has equations which are logarithmic equations because there is a logarithm in them. Part 2 has no logarithm, but it has exponents, and so it is referred to as an exponential equation. So you must recognize when you're given a logarithmic equation versus given an exponential equation. So our first questions are, given a logarithmic equation, rewrite it in exponential form. The pattern I use for this is I take the base across the equal sign to the power of 2, equaling what is referred to as the argument of the function. So this is written as 3 to the power of 2 equals 9. In part B, I would make the same pattern, kind of a little loop here. 4 to the power of 2 would be 16. In part C, 6 cubed would be 216. What I have written are exponential equations, so I converted the logarithmic equations into exponential equations. In part 2, I do just the opposite. They give me an exponential equation and ask me to write it as a logarithmic equation. The base is 5, so my logarithm will also have a base of 5. So this would be rewritten as log base 5 to the power of 3 equals 125. Really, log base 5 of 125 equals 3. Part B would be log base 6. 6 squared equals 36, so log base 6 of 36 is 2. Again, this is my logarithmic equation equal to the given exponential equations. Part 3 asks me to simplify the expression. Again, the terminology here to take note of is the word expression. Note, there is no equal sign. This is not an equation. These are all expressions. To rewrite these expressions equal to a number, I first want to take note that there is no base written on any of these logarithms. If a base is not given, you assume the base to be 10. If the base is 10, it is called a common logarithm, and therefore they will not write the base. They will assume it to be 10. So in this first example, I would rewrite this by saying log base 10 of 10,000 equals something. I will claim it x. In other words, this means that 10 to the power of x is 10,000. So what is x? Well, x would be 4 because there are 4 zeros. Therefore, log base 10 of 10,000 equals the number 4. The second example is log base 10 of 100, which you will calculate the same way and determine that it equals 2, meaning you are simplifying the expression. Part 4 is a similar question, but you can see the bases are now not 10. These are not common logarithms. In part B, I'm going to put an equal sign to x. In other words, I do not know what it equals, so I'm going to algebraically just call it x. If I converted this logarithmic equation to an exponential equation, I would write 1/4 to the power of x, kind of around the world or a little loop here, equaling 1/64. This is now a solving process similar to a prior page which we just worked on, in which I want both sides to have a base of 4. The left side would be 4 to the power of negative 1 to the power of x, and the right side is 1 over 4 to the power of 3. I could continue the solving process and write the right side of my equation as 4 to the power of negative 3. Once again, using the solving process we learned in the earlier topic of this lesson, when the bases are the same, I can set the exponents equal, giving a result of 3. So log base 1/4 of 1 over 64 equals the number 3. Moving down to part 5, this is actually probably an easier part of the connection to college algebra. It is asking us to find the domain. Well, the domain requires the argument of the logarithm to always be positive, or in other words, to always be greater than 0. So to find the domain, you would set the 5x plus 9 greater than 0 and then solve. Most of these will be relatively easy solving processes. It does ask me to write this answer in interval notation, so I'll have to take my inequality and rewrite it as a negative 9/5 to infinity, using parentheses on each end because it's a greater than symbol, not greater than or equal to. I do hope this lesson makes it easier for you to understand the beginning of logarithms. Again, you need to be very comfortable with transitioning from logarithmic equations to exponential equations as you progress through this chapter. Thank you for watching this recording and have a great day.